Hi students, so today we start lecture 65 in our course on aerospace engineering, and today I am going to discuss deceleration following the ballistic entry of the spacecraft into the Earth's atmosphere. This is lecture 65 in the course and I am Dr. Ranjan Ganguly. Now we have seen that whenever the spacecraft is trying to return back to Earth or it may be a different planet, what happens is that there are two things which are very negative for us. One is that the spacecraft has to go through a high deceleration. And this means that if it's a manned spacecraft, then the passengers inside it or the pilot are going to face levels of acceleration or rather deceleration up to 10 g. Now that's the maximum the human body can take. So we need to decide on designing the spacecraft such that it can take up to 10 g. Now, the second situation is that there is going to be high temperature which develops on the spacecraft body, and then that temperature is going to get communicated inside also. So, essentially, this is because of a very large amount of heating which takes place when the spacecraft enters the Earth's atmosphere. So, these are two main problems, and today we are going to look at the first problem, which is the deceleration problem, and we are going to try to create an equation which is going to help us predict the deceleration and figure out some ways by which the deceleration can be minimized, or I should say the maximum deceleration can be minimized. Now just to recapitulate, because we are using some of the equations from our previous lecture today, recall our previous lecture where we had the center of the earth, we had the spacecraft here. The spacecraft was moving around here and it had three forces: the lift, the drag and the weight, and the velocity v is given in this direction, and the spacecraft makes an angle theta with respect to the local horizontal line. Now we derive two equations of motion which you can very easily get. One of them is that lift minus weight cos theta, which is the weight in this direction, is equal to the force acting toward the earth, and the second equation is minus d plus w sine theta, which is in this direction. So that's the component of w in the direction of v, is equal to m dv by dt. So these are essentially coming from Newton's laws of motion. Now we are going to work with this second equation in developing the various equations today. So we start with this equation here: minus d plus w sine theta is m dv by dt. And in our previous lecture, I showed how from this equation we obtain this equation here after doing several different algebraic manipulations. Now in this equation, what happens is that the drag term is the CD term here, and the weight term is the G term here. So essentially you can realize that since drag is half rho v square SCD, the CD term will be the drag term. Now what's going to happen is that when you are returning to the earth, you are returning at a very high velocity. Typically it is hypersonic. So because drag is a function of v square, this term is going to be very large, and therefore drag is going to be much larger than the weight. And so we can neglect this g term here in this equation and we get this equation here, which then we proceed to solve. So let us look at this equation. We can express it in this form here, which I have put in the yellow box. So this form is much more amenable to integration. You can see here there is a dv square by v squared term. So we can integrate this and we will get a log to the base e term here, and this term is going to give me a term dependent on density. Now here one more thing we are going to assume is that lift is 0. Of course we are going through the ballistic entry system, and we are going to assume theta is constant so that we can do this integration. Now if we do that integration by assuming theta is constant, then this equation here, the integrated form, becomes this. So essentially what happens here is that when the spacecraft is entering the earth, the velocity is ve, or the entry velocity, and at that point the density is 0, and after some time the velocity is given by the generic velocity v, and at that point the density is rho. So this is our equation which relates the velocity after some time to the velocity at entry ve. Now we are going to use this equation today in some of our derivations, so let us just keep it in our mind and proceed further. Now let us come back to what we started this lecture with, and that was we were trying to know what is deceleration. So this comes out from looking at this equation here, which we looked at, the equation of motion for the ballistic entry for drag, and then we set the weight term to 0 because we are assuming that drag is much larger than weight, because of course drag is dependent on v square and v is very high. So I get this much simpler equation, minus d is m dv by dt, and from this I can get the acceleration term, dv by dt is minus d by m. Now this is the basic definition of acceleration, that it's the derivative of velocity with respect to time. So deceleration is of course going to be the modulus of this. So the deceleration value is simply drag divided by the mass. So we are going to try to figure out what is this quantity today. So the number we are most interested in is going to be maximum deceleration, but before that we know this is deceleration and drag is given by this value. So I can substitute this drag here and I get this value for dv by dt, the modulus or the absolute value of this, that is rho v square scd by 2m. So remember, rho is the density of air, v is the velocity of the spacecraft, s is the reference area of the spacecraft, and cd is the drag coefficient. Now if we look at this particular expression, we see that s, cd and m are typically going to be constant, so this equation is going to depend on rho and v square. So what happens is that when you first start entering the atmosphere, the density is completely zero, then the density starts increasing and the velocity is very high, so you are on this part of the curve, and then after some time the velocity actually starts decreasing substantially. So even though the density is going up, the dv by dt actually goes down. So this plot is about the deceleration g on the x-axis and the altitude h on the y-axis. So this curve is very important because what it tells us is that there is a certain maximum point here where the deceleration is maximum, and this is the point we are interested in, because do remember humans can take only up to 10 g, and therefore we must ensure that this should not exceed 10 g, because then the guys who are in the spacecraft are going to have a bad time. Even if you have an unmanned situation, the equipment and so on may not be able to take beyond a certain level of G. So that will come to you from the mechanical system designer, and you have to make sure that the deceleration is below that. So now we know this value dv by dt absolute value, let's call it delta, is given by this expression here. So we know from calculus that if you want to find the maximum point of such a function, we have to differentiate it and set it to 0. Now here the design variables or the variables for delta are rho and v. So this is essentially a two variable function maximization problem. So we differentiate delta with respect to t. So what happens is that scd by 2m come out because these are constants, and inside we get v square d rho by dt plus 2 rho v dv by dt. So essentially here I took v square and I differentiated the rho term, which gave me d rho by dt, and here I took the rho term out and I differentiate v square, which gave me 2v into dv by dt. Now from calculus I know that at the stationary point this should be 0, so I set this to 0. So therefore I can drop this constant out and I can simply write this equation here, that the term inside the bracket should be 0. Now from this equation I get this equation here, which is obtained after cancellation of one of the v's here. So this is the equation. Now we are going to proceed further from that. It essentially links the derivative of density with respect to time to the derivative of velocity with respect to time, and tells us that when this condition is met, you are going to get the maximum deceleration. So let's proceed from this equation here. So now we have this equation. Let's return to our fundamental definition of dv by dt, which was minus d by m. I derived that a couple of slides ago. Now here I put d from the usual expression, half rho v square scd. So I get minus rho v square scd by 2m. Now what I do is I take this equation here, v d rho by dt, and on the right hand side I substitute this dv by dt which I just obtained. So I substituted that here. The two negative signs resulted in a positive sign, and then after some cancellations I get this equation here. The 2 cancels out, and so I get rho square v square scd by m. Now from this equation I can write straight away that d rho by dt is rho square v scd by m. So I obtained a very nice expression for the density derivative which we are going to use further. So now what I'm going to bring into this system is the exponential atmosphere. So recall from our previous lecture, the exponential atmosphere means that rho by rho 0 is e to the power minus g0 h by RT, which is e to the power minus zh, where z was g0 by RT. So what I can do is I can write rho as rho 0 e minus ch, and this allows me to differentiate rho and express the derivative with respect to h. So I get d rho by dt is minus rho 0 z e minus ch. That's simply the differential of this, and I also get dh by dt here. Now I can look at this expression and immediately realize that this rho 0 e minus ch term here is rho, so this becomes minus 0 dh by dt. So now this is another equation. So after I included the exponential atmosphere, d rho by dt can be expressed in terms of dh by dt, and the parameters are z and rho here. So let us continue on our maximum deceleration journey. Now we have the expression for d rho by dt from a couple of slides before. We also have the expression for d rho by dt in terms of dh by dt from this. We also know from our previous lecture that dh is minus ds sine theta. So if you are not familiar, just go back and check this out. This is just coming from the geometry. S is the path variable along the path in which we are traveling. Now from this equation I can differentiate with respect to time, and I get dh by dt is minus ds by dt sine theta. So all I have done is divided this equation by dt, and then I know that ds by dt from basic kinematics is velocity. So that's the derivative of displacement with respect to time. So I get minus v sine theta. So from this I can get d rho by dt is z rho v sine theta. So essentially I can take this equation here, and all I have done is that I have substituted dh by dt here. So that's given me z rho v sine theta. The minus and minus have resulted in a plus value. So I have two equations which are telling me what is d rho by dt, one equation here in red and one equation here in blue. And so I'm going to equate this red equation with the blue equation, and when I do that, again I can do one or two cancellations. So after I cancel for rho and v, I get z sine theta on this side, and on this side I get rho scd by m. So this is the equation we are going to now carry on further. So this is the equation, and from this equation I can get rho is m by scd z sine theta. Now this equation tells me that the density at the maximum deceleration point depends on these parameters. So it depends on the mass, on the reference area, on the cd or drag coefficient of the spacecraft, on the z value, and on the angle which you are taking for the entry. Remember, here in this derivation the theta value is constant. So let's take this equation for rho, and now we are going to go back to our formula for the maximum deceleration value, or delta max. So dv by dt max is going to be rho v square scd by 2m. That was the general formula, and in that I substitute basically this formula here. So I get this formula here. So when I substitute rho here from this equation, I can immediately get a cancellation of scd and m. So essentially I get much simpler form. I simply get v square z sine theta by 2, and therefore just to write it out again, delta max which we were searching for is equal to v square z sine theta by 2. So that's the equation to keep in mind, which is telling you what is the maximum deceleration value here. So We now know the density at the point of maximum deceleration. We also, from our previous derivations in the last lecture, and I showed you this equation before, know the ratio of V by VE. Now, when I compare these two formulas, suppose I put rho into this equation here for V by VE, I will get a bunch of cancellation because you can see here m by SCD z sine theta is also here. So all the terms actually get cancelled out, and the only term which remains is the minus half term. So V by VB is e to the power minus half. Very compact and interesting formula which tells you that the velocity is actually changing in an exponential manner, and it's actually changing with respect to the root of the exponential manner. So remember, v is the velocity at a given point here of point of time. V is the entry velocity when it entered the Earth's atmosphere. So that's how the velocity is going to change. So delta max, then this was the equation we had from our previous slide, and now when I put in VE here, I get this equation here. So the E term comes in here in the denominator. So this of course gives us an equation which we can use. We can know the V entry value, the velocity of entry, say in meters per second or kilometers per second. We can calculate Z. If we know theta, then we can very easily obtain this value. Now, of course, some of you may have forgotten what is E. E is a number 2.718 and so on. Generally, we can use 2.718 for most of our numerical work. And E is an irrational number. It's also sometimes known as the Euler's number or the Napier's number. So just like you know pi is 3.519, you need to remember this also, or rather pi is 3.14159. So let us now summarize some of the things we learned today. We saw that this derivation could be done. That is the equation I have shown in yellow. dv by dt max is ve square z sine theta by 2e, where z is g0 by rt. So looking at this equation, we see that this maximum deceleration depends on the entry velocity, on the angle at which you are entering, and on this z value. Now the planetary conditions come in through the z value because r reflects the nature of the gas you are dealing with. G0 of course is the acceleration due to gravity. Now this equation is giving me two equations, or two ideas rather, that the maximum deceleration is directly proportional to ve square and also directly proportional to sine theta. So if I was entering the earth at a very high speed, which is generally the case, then this deceleration is going to be much more. So for example, if I were to enter from a parabolic or hyperbolic trajectory, which is much faster than say a circular trajectory, then I would have a higher level of deceleration. Now that is something which happens by nature. Whatever the entry velocity is going to be there, because that would depend on the particular mission of the spacecraft which has gone out in space and is coming back to Earth. So of course the proportionality with ve square is there. You may try to reduce your entry velocity as much as possible. The second possibility is that you can try to enter at a very small angle. So that's something which is more practical. So the angle should be as shallow as possible. So maybe if you enter at 2 to 3 degrees or 5 degrees instead of 10 to 15 degrees, you are going to have a much better time as far as the deceleration levels are concerned. Again, remember this is important because humans cannot tolerate a deceleration beyond a certain point, and so if your design is such that this spacecraft is subject to deceleration of more than 10 g, then the passengers in it may have various deleterious health consequences. So let us summarize what we learned in our lecture today. We saw that the deceleration term, which is the absolute value of dv by dt, is given by d by m, and that's very important. And we also got the equation for the density at which the deceleration is a maximum. This corresponded to the maximum deceleration value of v square z sine theta by 2, and also we could express it in the form ve square z sine theta by 2e. So this gives us an equation through which we can calculate the maximum deceleration. Like I mentioned before, that is a useful ingredient in the design process. because here you are taking care of the people who are in the spacecraft in case you have a manned spacecraft. For an unmanned spacecraft, you need to find out what is the exact maximum G which the equipment and the systems can take, and you need to design for that. So this was the lecture for today where we learned about maximum deceleration, and only one thing remains in this spacecraft dynamics, which is the heating, and that's what we are going to study in the next lecture, where we are going to look at the heat generated by the typical spacecraft and why we often prefer blunt bodies when we design these kind of spacecraft. So that's something we'll look at in the next lecture. See you then.